Hello. Today in this video, I'd like to talk about the electrical concepts of resistance and Ohm's law as applies to electrical circuits. To do that, we're going to describe resistance and its relationship to the properties of material. We're also going to analyze the relationship between electrical potential, current, and resistance, otherwise known as Ohm's law. Let's get started with resistance first. Now resistance, it's in the name. Resistance is the ability of an object to resist the flow of electrical charges. Every material has charges a part of it. If we imagine a wire here that we're applying a voltage to, an electrical potential, that potential pushes electrons down into that wire. But since there's already charges in the wire, they're going to experience a repulsive force because like charges repel. And so there's going to be some resistance to that flow of electrons in that wire. Now this resistance depends on a few things. We're going to look at it mathematically in a second. But the first is just a property of the material. It's called resistivity. And we represent resistivity with the Greek letter rho. And it depends on the material that you look at. In your New York State Physics reference table, on the front, there are a list of resistivities for different materials. Ones that we know we make wires out of tend to have low resistivities, like copper, gold, and silver. Whereas ones we don't make materials out of that are in circuits much, like aluminum, nichrome, and tungsten, they have high resistivities, and that just depends on the material that we have there. But there are other things that affect the materials that are going to be in a wire. Imagine taking a wire here. Let's go ahead and draw a really thick wire versus a really thin wire. We'll call it thick, and we'll say one is thin. Imagine you're trying to push 10 electrons through those wires. Which one is it going to be easier to push those electrons through? Well, obviously, if I have to push 10 electrons, I'm going to want to use the thicker wire rather than the thin one. If I'm trying to push 10 electrons through this little tiny, teeny wire, it's not going to be as easy to do that. There's going to be more resistance to that motion than there is in a very thick wire. So the one thing it depends on is cross-sectional area. So one other factor that impacts resistance is called cross-sectional area. The reason why it's called cross-sectional is because this is like a cross-section of a wire. You're just looking at that one section that makes a circle there. Now to calculate the cross-sectional area, you got to think back to math, maybe geometry or algebra, and remember the area of a circle is pi r squared. And we'll take a look at an example of that in a second. The other thing that it depends on, of course, is the length of your wire. If we draw a small wire here, the further down that wire I go, the more charges that line up to resist that flow. So the longer the wire I want to get, the more resistance we have. So number 2 is going to be length. So both cross-sectional area and length affect the resistance in a wire. Let's take a look at that mathematically. Mathematically, we can say that the resistance in a wire, R, is equal to rho times L divided by A, where those are our three variables we've seen. Rho is resistivity. And if you look in your reference table, you'll notice they're all measured in ohm meters. L is our length, measured in meters, and area, measured in meters squared. So you notice the unit for R, or our resistance, ends up being ohms. We'll spell that as O-H-M. Now, let's take a look at how to solve these. Go ahead if you'd like, try the example problems on your own, pause your video, then come back, take a look and see how you did. So taking a look at our examples, we have a 10 meter length copper wire at 20 degrees Celsius. The radius of that wire is 1 times 10 to the minus third meters. We want to determine first the cross-sectional area of the wire, and then finally the resistance of the wire. Well, remember that cross-sectional area for a wire, A, is equal to pi times r squared. We go ahead, we know pi is 3.14. You can just do that in your calculator. Plug in our r as 1.0 times 10 to the minus third meters. Solving that out in your calculator, looks like I get 3.14 times 10 to the minus sixth meters squared as my area. Now we're going to need that below because to calculate the resistance, big R, is equal to rho times L divided by A. Now this is for copper. And so if we look up the resistivity of copper in our reference table, it's 1.72 times 10 to the minus 8th ohm meters. That's going to be times our length, which is 10 meters. And then finally, divide that by our area we calculated, 3.14 times 10 to the minus 6th meters squared. Going ahead, plugging those numbers in my calculator, I end up getting 0.055 ohms. Okay, let's look at our last example problem. We have a 3.5 meter length of wire with a cross-sectional area of 3.14 times 10 to the minus 6 meters squared. And we know the resistance is 0.0625 ohms. Now, we want to determine the resistivity of the wire and then use that to determine what material our wire is made of. Same equation we've seen before. Our R is equal to ohms, rho times length divided by A. Go ahead, plug in big R, 0.0625 ohms equals my resistivity times the length of 3.5 meters, and divide that by my area, 3.14 times 10 to the minus 6th meters squared. I go ahead, solve that in my calculator. I end up getting a resistivity of 5.6 times 10 to the minus 8th ohm meters. If you look back on your reference table, 5.6 times 10 to the minus 8th matches up well tungsten, which is element W. Okay, let's go back and take a look at one thing on that reference table. Kind of caught my eye. Take a look up here. See how they say those are resistivities at 20 degrees Celsius? That should tell us something. It should tell us that resistivity changes with temperature. I want you to think about that for a second. Why would resistivity change with temperature? Well, one thing we want to know is that as the temperature of a resistor increases, the resistance of that wire also increases. It is harder for the electrons to flow through a hotter wire than it is through a colder wire. You've probably experienced this. On a hot day, if you get your cell phone or your computer really hot, it doesn't work as well. Or if you've noticed your computer ever overheating before, it's a bad thing for electronics because its resistance increases and it doesn't work quite as well. Now think about why that might be. If you have a material, it's made of lots of different teeny tiny particles, electrons, protons, atoms, lots of things there. If I heat that up, if I increase the temperature, I increase the motion or the kinetic energy of those particles. And so those particles start flying even more around and around. And if I'm trying to push electrons to the material, it's going to be way harder to get them to go through there if all of those particles are moving a lot faster. That increases then the resistance of my wire because it increases the repulsion by those atoms in the material. Now, one thing I love to talk about and make sure that we understand is that resistance is not always a bad thing. We talk about it like it's a bad thing. Oh, my computer overheated and so it doesn't work quite as well. But we actually use this all the time. And one place you use it is in your toaster. If you've ever looked in your toaster, there are these nice, wonderful red-looking, not red thing, they're red because I use my pen, but these kind of foldy-looking things that get red when you go ahead and heat up your toaster. Those are a type of resistor, and we use it because when a resistor's temperature increases, the resistance goes up and it produces heat. So a hot resistor gives off heat, and that's actually useful. It toasts our bread. So if we're making a toaster, we would want to pick a high resistivity material. And any guesses what material that is? For those of you who just pulled out your reference table, you would be right. Oftentimes, toasters are made out of nichrome. At least the filament in the toaster that heats your toast with is made out of nichrome because nichrome has a high resistivity, and that lets it let off heat to heat your food. Well, that's resistance, but let's see how that relates then to some of the other variables we've seen in this unit about electricity. I'm talking, of course, about Ohm's law. So, Ohm's law tells us that as the resistance of something increases, the current flow in that object is going to decrease. It's harder to push the electrons to the material, so as the resistance goes up, so the current decreases. This means these quantities are inversely related. Likewise, as the potential difference increases, I have a greater potential, more energy I can get when I push those electrons through a material. That means the current is going to increase. That means those materials, or those quantities, are directly related. That leads us to Ohm's law, that V is equal to IR. So our electric potential is our current times our resistance. Now, nice easy equation. What I'd like you to do is pause your video now, try the next few practice problems, come back and take a look at the answers here. So, getting to those example problems. We have a 12-volt battery that causes a 2 amp current to flow through a copper wire. What's the resistance of the wire? Well, V is equal to IR. We know that we have a 12-volt battery pushing a 2 amp current through my wire. I want to find the resistance. Plug and solve. You can almost do this one without a calculator. Our resistance must be 6 ohms. Next, I have a 120-volt outlet, applies a difference in electrical potential energy across a toaster with a resistance of 14 ohms. I'm going to calculate the current. Once again, V is equal to IR. 120 volts equals I times 14 ohms. Plugging that into my calculator, I get 8.57 amps. And then finally, a charge of 3 coulombs moves through a circuit with a resistance of 6 ohms in 0.5 seconds. What's the potential difference in this circuit? V is equal to IR. I know that, but I don't know the current directly. Instead, I need to calculate the current first. Don't forget all those equations we've seen before, that current is the change in Q divided by T, my charge divided by time. So I take my charge, 3 coulombs, divide by the time, 0.5 seconds, to get that the current, well, it is measured in amps, but it's going to be 6 amps. And not my friend Gil. Once I have that 6 amps, go ahead, plug that in over here in V equals IR. I know that my current is 6 amps, my resistance is 6 ohms, so my electric potential difference must be 36 volts. Okay, folks, that's resistance and Ohm's law. Thank you very much, and I'll see you guys later.